Moving on to electrochemistry. So we've talked about a lot of different types of reactions, but we haven't actually talked about how to do something practical and useful out of them. But electrochemistry is one of those where we will do something practical and useful with the reactions. We're going to start by going backwards to remind you what redox reactions are and about oxidation numbers and what it means to be oxidized and reduced. So in this given reaction, we start off with magnesium, which is solid magnesium with a 0 charge. That magnesium becomes Mg2+. Mg2+, oxidation number +2. So from 0 to +2, magnesium lost electrons in that transaction. Magnesium was oxidized in this reaction. Conversely, hydrogen went from a +1 to a 0 over here on the products side. +1 to 0, it means it was reduced. Hydrogen was reduced because it gained electrons. There are two acronyms that you may see surrounding redox reactions. One is oil rig. That stands for oxidation is loss of electrons, and reduction is gain of electrons. Another one you may have heard is Leo Ger. Leo the lion says Ger. Losing electrons is oxidation, and gaining electrons is reduction. So if we take a closer look at that same redox reaction, all redox reactions can be written as half reactions. If you include just the magnesium part, you get Mg yields Mg2+ plus 2 electrons. That is our oxidation half reaction. The oxidation half reaction always loses electrons. The reduction half reaction always gains electrons. So if we have the hydrogen part of the equation overall, that's the reduction half. If you sum those reactions together, your 2 electrons cancel out, and so that gives you your overall reactions. Electrons are never shown in the overall reaction. Something to note is that you can never have oxidation without reduction. They have to be happening in a system together. So if you were to see only the magnesium half of this reaction, that's not the complete picture. That's only half of what's going on in a system. Here's another redox reaction for your viewing pleasure. Something to note here is SO4, that's sulfate. That's just partnered up with copper. That's aqueous copper sulfate. It's a soluble compound. So SO42- and SO42- this aqueous zinc sulfate, the sulfate does not get oxidized, the sulfate does not get reduced. But the metals in the reaction are oxidized and reduced. We're going to see that metals are frequently the focus of these reactions. So zinc goes from a zinc 0 to a zinc 2+ in zinc sulfate. There's the oxidation half reaction. Copper goes from a 2+ to a 0. Here's the reduction half reaction. I can't help that some of the terminology around redox reactions is confusing, but because zinc gave electrons to copper, zinc is called the reducing agent because he assisted copper in being reduced by giving the electrons to copper. On the other hand, copper, Cu2+, copper took electrons from zinc, so that makes copper the oxidizing agent. Yeah, real strange, I know. The thing being oxidized is the reducing agent. The thing being reduced is the oxidizing agent. There's another little, not acronym, but another little phrase that sometimes helps students remember things. Me-red-cat, as in metals reduce cations. Metals give electrons to cations, and cations take electrons from metals. Cations oxidize metals. We'll say it that way a few times. Here's a sentence that describes a redox reaction. Copper wire reacts with silver nitrate to form silver metal. What's oxidized? So first, you need to come up with a balanced equation. Copper wire, that's copper solid, with silver nitrate, Ag plus is the important part, the oxidation reduction part. It will form silver metal. So we've got silver metal over here. We're going to create the stable copper 2+ ion. Note that 2 silvers are needed to react with copper because silver has a +1 charge and copper has a +2. So to balance out the charges, you're going to need 2 silvers. Here's one half reaction. Here's the other. Which is which? Copper is giving up electrons. So copper is oxidized. Copper lost electrons. Silver was reduced. Silver gained electrons in that transaction. Let's check out a little video of how this actually happens in solution.
Displacement reactions are among the most common redox reactions. For example, a metal in a compound can be displaced by another metal in the uncombined state. When metallic zinc is added to a solution containing copper 2 sulfate, it displaces copper 2 plus ions from the solution. Zinc reduces copper 2 plus ions by donating 2 electrons to it, producing copper metal and zinc 2 plus ions in solution. Note that copper metal is depositing on the zinc bar. Also, during the reaction, the solution loses the blue color that characterizes the presence of hydrated copper 2 plus ions. Let's zoom in to view the reaction on a molecular level. Zinc atoms enter the solution as zinc 2 plus ions, losing 2 electrons. Zinc is oxidized. The electrons are gained by copper 2 plus ions, which are converted to copper metal. Copper 2 plus ions are reduced. Similarly, metallic copper displaces silver ions from a solution containing silver nitrate, AgNO3. Each copper atom reduces 2 silver plus ions by donating 2 electrons. Note the silver metal is depositing on the copper wire. Also, during the reaction, the solution turns blue due to the presence of hydrated copper 2 plus ions. Let's zoom in to view the reaction on a molecular level. Copper atoms enter the solution as copper 2 plus ions, losing 2 electrons. Copper is oxidized. The electrons are gained by silver plus ions, which are converted to silver metal. Silver plus ions are reduced.
So we have to keep that sort of microscopic view in mind the whole time when we're talking about these sort of reactions. All right, one more question about this reaction. Which one is the oxidizing agent? Silver plus, because that's the thing being reduced. This Ford reaction is spontaneous. What that means is silver would rather have electrons and be a metal than copper. It is more energetically favorable for silver to be in the solid state than copper to be in the solid state. The reverse reaction is non-spontaneous. It is not spontaneous for electrons to leave silver and cling to copper. Non-spontaneous.